The talk will be given by, the paper will be presented by Mohammad Alizadeh, MIT. He's an associate professor there and a member of CSAIL. Before that, he obtained his PhD at Stanford and spent a couple of years at Data Center Working Startup and Cisco. And you were also the winner of the Rising Star Award, 17, right? Yeah. Yeah, I guess.
17 or 18.
A long time ago, yeah, right, okay. So, with that, the floor is, oh, by the way, the paper is called M3, Accurate Flow Level Performance Estimation Using Machine Learning. The floor is yours.
Great. Thank you very much for the introduction. Last time I gave a talk at SIGCOMM' was, I think, 10 years ago. So it's great to be on the podium again. Where's the... Is it this one or this one? That one. All right. Yes, I'm excited to be here to tell you about our work on M3, which is a system for accurate flow level performance estimation using machine learning. This is joint work with a great cast of students and collaborators at MIT, University of Washington, and Microsoft Research. I just want to give a quick shout out to the two lead authors of this paper, Channing Lee and Arash Nasraswani, who unfortunately couldn't be here due to visa issues. So to set the stage for this talk, data center network operators often need to predict how the performance of their network is affected by various changes, such as a new workload, a change in network topology, or the network configuration. And the most common tool for answering these kind of questions today is to do packet-level simulation, such as NS3. So NS3 takes as input a network topology and configuration and a workload, and it runs a detailed packet-level simulation from which you can extract any performance statistic, like things like packet loss ratios, buffer occupancies, flow-level delay, and jitter. But NS3 is very slow. A simulation of even a modest-sized cluster of, say, 6,000 hosts takes 10 hours for just 5 seconds of simulation time. So as a result, there's been a lot of recent work on accelerating network simulation. And I'm going to broadly categorize them as efforts to increase the level of parallelism of exact simulation, and then techniques for more approximate simulation, for example, using machine learning. But all of these approaches are still packet-level simulators. And any packet-level model has inherent scalability limits for high-speed, large-scale networks. And this is a problem that's just going to get worse over time as networks become faster and larger, because the number of packet-level events in the network is simply going to explode. So do we really need packet-level simulation? So we argue that for a lot of questions we're interested in, packet-level simulation is actually overkill. Many questions in particular are not about tracing the behavior of specific packets or even specific flows. They're about aggregate performance statistics, like tail latency, network throughput, loss rates, short and long flow completion times, and how these things change due to changes in workload or design choices. So can we raise the level of abstraction for answering these kind of questions without sacrificing fidelity? So to explain how we're going to go about this, the starting point is, let's think of the network simulator as implementing abstractly this sort of end-to-end function. It's a function between inputs that are the network scenario, basically the network topology and configuration, and a workload, to some outputs, performance statistics that we care about. So just for concreteness in this work, we're going to focus on flow completion time slowdown. Flow completion time slowdown is defined as the ratio between the completion time of any flow and the smallest possible completion time that it can have in an unloaded network. And it's a typical sort of performance measure for understanding data center transport performance. So we have this function. And kind of a simple question I want to ask here, can we actually just learn this function end-to-end through data? Can we use supervised learning to learn this function from training examples? So this is conceptually straightforward. But the problem is that this is a very complicated function. So if you think about how a packet-level simulator implements this function, it goes through this low-level packet-level interactions, models all of them, updates this kind of huge internal state machine. And from all of that, you can then get this performance statistic. And it's not really clear if there's some higher level representation of this function that we're going to be able to learn. And even if we figured out a high level representation, how do we collect training data for learning this kind of function? As I mentioned, even one simulation of a relatively modest size data center topology takes hours. So how are we going to collect enough examples to kind of learn this function from data? So M3 is a system that tackles these challenges to train a model for accurately predicting flow-level performance in data centers very quickly. M3's model takes as input a network topology, a workload, and a set of configuration parameters, and it predicts the full completion time slowdown distribution of the network that would have been produced if you ran an NS3 simulation. But M3 does this much faster, obviously, than running the simulation. For example, in that 6,000 host topology that I mentioned, M3 is about 1,200x faster than running NS3 with an estimation error that's less than 10%. So this takes you from a 10-hour simulation to something that's less than a minute. OK, so how do we do this? So I want to start with this picture again of a data center network. So as I mentioned, learning this kind of end-to-end function for arbitrary network scenarios, arbitrary topologies and workloads is very challenging. So M3's first idea is to reduce the problem to a much simpler building block that we call a path-level simulation. So in a path-level simulation, we're just going to focus on one path in this topology and the flows that are along this path. So let me prune the rest of this network. And I'm further going to prune some of the traffic here by making a simplifying assumption, which is that the flows that do not intersect any link on this target path have only second-order effects on the performance of traffic on that path. So this gives us what we call a path-level simulation. And every path-level simulation in M3 looks something like this. It's a chain of links, a set of flows that traverse the entire path that we call the foreground flows, and a set of flows that are cross-traffic, basically, and traverse some link on the path that we call the background flows. And the goal of any path-level simulation is going to be to estimate the FCT slowdown distribution of the foreground flows on that path. Okay, how do we use this? So we do this path decomposition and aggregation. So when we have a network scenario, we sample some number of paths at random, think like hundreds of paths or thousands of paths, and then we get all these different path-level scenarios. We estimate the performance of the foreground flows on each of these paths, and we aggregate the results to get a network-wide estimate of performance. So path decomposition is giving us two benefits here. First, it's reducing the problem to these path-level simulations, which are a much narrower space of network scenarios, where I'm going to show you we're going to actually be able to learn a high-level model of that end-to-end function for. And second, we get this natural parallelism because we're estimating performance of these paths all in parallel. They're all independent. But I've made a bunch of assumptions. So is path decomposition actually accurate? So here's an experiment with sort of realistic workloads based on measurements from production clusters that shows you that path decomposition is not a bad approximation. So here we looked at three scenarios, three of these kind of scenarios from Meta's production traces. And first, we're going to just simulate the entire scenario using NS3, so on a full topology. And second, we take for each scenario and sample 500 paths at random, and we estimate the performance of these path-level simulations using NS3 for now. So I'm still just using NS3, and I'm going to call this NS3 path. So I can now compare the tail latency predicted by running NS3 on the full topology with this NS3 path approach. And here, what I mean by tail latency is the 99th percentile FCT slowdown of flows on any given path. So here's the distribution of the relative error of NS3 path compared to NS3 over all these paths across these scenarios. And you can see that the approximation error is not that bad. So the table actually shows you the median approximation error in any of these scenarios is less than 6%. But so far, I'm still doing packet-level simulations for the path-level performance estimates. And so that gives me some speed up still, because I can now do a bunch of these past simulations in parallel, but it's somewhere between 3 to 14x, and we're hoping for much more speed up than that. So the second idea in M3 is to estimate the path level performance with machine learning. And this is that supervised learning problem that I was talking about. But I still have this problem of how to represent this to an ML model. Even a path level scenario can have tens of thousands of foreground flows and many more background flows. So the second idea in M3 is to use a flow level simulator to extract a rich and compact set of features for its machine learning model. So to tell you how this works, M3's flow level simulator is a standard max-min flow level simulation. So in these simulations, there are no packets. Flows are represented as fluid flows, sending at time-varying rates. The rates are computed to be the max-min fair rates for those flows, given the active flows in the network at any point in time. So this is just max-min fairness is an approximation of congestion control. So that's why we're doing that. Events are flow-level events, so flow arrivals and departures, and there are no queues in the simulator. So because we ignore all the packet-level detail, FlowSim is actually very fast. So a typical flow-level simulation in M3 takes less than a second. But FlowSim is a coarse approximation, and it's not going to be very accurate. So here we're seeing the comparison of the FCT slowdown distributions predicted by NS3 versus FlowSim. And you can see that even though the estimates are not bad for larger groups of flows, so these are the large flow size ranges, for short flows, this is going to be a very poor estimate because we ignore all the queuing delay. We ignore all queuing effects. And that's going to be the dominant determinant in performance of very short flows. So despite this, I want to show you that you can use all this flow completion time information produced by a flow-level simulator to provide a very rich representation of a path-level network scenario. So here we run these path simulations in FlowSim, and then we're going to summarize the FCT slowdowns that we see into this compact feature map. So this is what the feature map looks like. It's basically a matrix. The rows correspond to different flow size buckets. So flows, small flow size ranges all the way to larger flow size ranges. And the columns are different percentiles. So every entry is basically the FCT slowdown distribution at a certain percentile for a certain size range of flows. Okay, so why this feature map? So let me show you that actually this feature map captures many of the important characteristics of a workload that determine flow completion time performance. So for example, if I look at situations where I have these network scenarios and I'm varying the level of load, you can see that these feature maps are going to change in a very logical way. So as you go up in load, the flow level simulator is going to tell you that you're going to see these higher slowdowns, and you're going to see them at higher percentiles more, and for larger flows more. That's what all that red stuff is. What about something a little bit more subtle, like changing the burstiness of the traffic? So if I change the burstiness of traffic, so here I'm controlling this shape parameter that, of the flow interarrival time distribution. And basically, as I go up in burstiness, I can see the FCT slowdown distributions of the flow level simulator will reflect this increased contention. So a good way to think of M3 is it trains a machine learning model to learn the differences between a flow level simulation and a packet level simulation. It essentially corrects the approximations made by this flow level simulator. So when we run a path level scenario, we get all these feature maps. There's one for the foreground flows, and there's a feature map for every hop for the background flows. We give all of that to a machine learning model, along with a network specification. So these are all the things that we kind of ignored in the flow level simulator. What congestion control protocol is running? What's the buffer size? And other things. So the machine learning model looks at this network specification and that context, and then it will predict what the flow completion time slowdown distributions would have been under NS3. And here's an example of that. So this is the same scenario as before. The blue markers are now M3's predictions of what the distribution should be at different percentiles. And you can see that it now aligns well with the pink line. So that's NS3, the ground truth. So for example, for the short flows, M3 knows that flow stems estimates are underestimates of reality, and it corrects it, increasing the distribution, shifting the distribution. Okay, so how do we train this model? We train it on a diverse set of synthetically generated scenarios. Remember, we're only dealing with path-level simulations now. So we create as many different path-level scenarios as we can come up with. So different number of hops, different flow size distributions, different flow interarrival time distributions. And M3 is trained to learn the impact of parameters for describing a network configuration. So every time we sample a random point in that parameter space. So this means like choosing a different congestion control protocol, the parameters of that protocol, and so on. Importantly, we only train on this diverse mix of synthetic scenarios, and then at test time, we want to see if the model can generalize to new workloads and topologies. So all the test results are based on empirically measured traffic distributions from data centers. So here's an example of our accuracy evaluation. So these are various production workloads based on Meta's data center network traces. And this is the relative prediction error of M3 compared to NS3. So you can see that the relative error is not bad. You know, at the median, it's well under 10%. And even sort of at the higher percentiles, it's still a relatively good approximation. Just as a reference, here's a state-of-the-art sort of approximate network simulator published last year that does not use machine learning. It does a sort of a decomposition of the network-wide scenario into a bunch of independent link-level simulations. And M3 is more accurate. So it reduces the average error by about 2x compared to Parsimon. M3 is also very fast. Here's the run times compared to NS3 and Parsimon for all these scenarios. Overall, it's about 5.7x faster than Parsimon and 3 orders of magnitude faster than running NS3. So I want to be clear, M3 is by no means a general network simulator. It's a performance model. It assumes static flow routes, the current version, so you can't really model dynamic routing strategies like flowlets and packet spraying. It predicts some performance statistic, like the distribution of flow completion time slowdown. It can't give you per flow or per packet information. And it's learning the impact of network parameters from training examples. So this is not going to be able to tell you what happens for, say, a new congestion control algorithm that it hasn't seen in training data. So just to sum up, M3 is a fast and accurate method for estimating flow level performance, and it has these two key ideas: path decomposition and using a flow level simulator to extract features for its machine learning model. And this second point, I think, is actually kind of a pretty general idea that I think could be useful in other settings. So if you're trying to learn a performance model or learn model a complex system, and you have some reference system that is a crude approximation, training a machine learning model to kind of translate between this crude approximation and the real system seems to be a promising approach. And in M3, it was quite successful. So with that, I'll stop there. Thanks for your attention.
Thank you, speaker. Last question, Matt.
Matt Rowan again. Thanks for a lovely talk. I really enjoyed that. I'm going to show my age here, but I feel like this path decomposition where you have sort of loose second-order relationships is really reminiscent of some of the work that people like Frank Kelly did on reduced load approximations, so you're obviously aware of that.
Absolutely.
Some of that gives you some insights about when that sort of approximation is going to work and when it's not. I wonder if that's guided why you're sort of focused on data centers, or is it just the place that you really want to work?
I think it's both. Yeah, no, absolutely. So, you know, this questions of, you know, when can we basically, it's kind of like all these product form, factorized models. No, I think these kind of workloads, you know, in data centers, there's so much statistical multiplexing happening that it kind of seemed natural that this actually would be a place where, you know, these things apply. You have mixes of sort of short and large flows, but Yeah, so we kind of suspected that these would be good approximations. Even if you look at the Parsimon paper, which actually our team kind of worked on before that, that was even taking this to another extreme of just do independent link level simulations. And even that is a relatively good approximation. I think it really is based on that theory that this actually can work. Cool. Yeah.
Thank you. Next question.
Thanks for the insightful talk. So I'm Shuai Hu from Huawei, and I would like to ask a question about the application scenarios of this M3 simulator. So in your opinion, will M3 be a good tool for studying or comparing different conjecture control algorithms?
Yeah, that's a great question. So M3 is, as I said, it's if you want to do some kind of design space exploration, so yeah, you want to compare a bunch of different congestion control protocols or vary a lot of parameters. There's actually results of this type in the paper that I didn't go through. M3 gives you a very fast way of getting the trends. And kind of like figuring out like what's actually going to be the interesting stuff to maybe zoom into and simulate, maybe more in a more exact way. There is another thing that we're working on, but it's very much kind of work in progress, where if you have a model that can predict performance and it's very fast, you can now imagine using it in the inner loop of an optimization process to try to tune, some aspect of your network. So that brings up a whole set of interesting challenges of how to deal with approximation errors and model errors, but I think that's kind of an interesting thing as well.
Okay, thank you.
We've got time for one more question.
Okay, great talk. Thanks, Mohammed. Ingzen from Meta. My question is about the workflow featureization. So it seems like, how much do I need to know what kind of, roughly what type of workload features do I need to care in order to generate training data for this model?
Yeah, so, so these workload features, that I talked about. So for anything flow completion time related, this is very natural, because basically it is the flow completion time that is observed in a packet, in a flow level simulation. So it's kind of exactly what you're trying to predict, except shifted, warped, in some sense. That's kind of what I was trying to say. So for this, it seems very natural. But if I was thinking more generally, why would flow completion time information over different flow size ranges be a meaningful feature? It's because, as you know, flow completion time for different size buckets basically gives you a profile of the latency and throughput characteristics of the network. You look at the lower size ranges, those are the latency characteristics of the network. You look at the upper size ranges, those are the throughput characteristics of the network. And this is a very sort of compact way of expressing the throughput and latency characteristics that you're observing due to a workload. So I think that there's a good chance that this is quite a universal feature, but there's still a lot more work to do to kind of try to predict other kinds of statistics with it. But that's kind of the intuition that we have.
Thank you. Let's thank Mohammed again.